Last semester, when we talked about conditional distribution, we were working with discrete random variables. There we had learned that if x and y are discrete, then the conditional PMF of one random variable given the other of x given y equal to y was defined as probability x equals x given y equals y, which by definition of conditional probability is, and we had defined it only for those values of little y for which the denominator does not vanish. Now in this semester we want to do a similar thing, but when x and y have joint density. Then of course we do not want to talk about conditional PMF, we would like to talk about conditional density. And if we just try to imitate this definition, we will be in trouble because now the denominator has probability 0 because y has a density. So whatever little y you take, I always have probability y equal to 0. So we need to employ a little roundabout trick, a little heuristics. By heuristics we mean some argument which is not entirely rigorous, but still it leads us towards the correct answer, which we can later justify rigorously. In order to understand the heuristics, let's consider this. If x has PMF, some x has PMF fx, what does that mean? Probability that x equal to some little x is f of x. Now let us see what happens if it has density. If I make this statement, then is it correct? No, because this will always be equal to 0. But there we saw one intuitive explanation, and that was, if we take x approximately equal to x, in other words, x lies in a little neighborhood around a, from x minus epsilon by 2 to x plus epsilon by 2, then this is approximately fx times epsilon. So we had seen this intuitively by considering the area of a very narrow strip drawn over this interval. Now let's return to our discussion of this conditional probability. We have just now seen that if x and y are jointly continuous, having a density, in that case this probability will be 0. So as such it is not defined, but I will employ these heuristics. I will replace the equalities by approximate equality. When I write approximate equality, you understand it lies between x minus epsilon by 2 to x plus epsilon by 2. Similarly, y minus epsilon by 2 to y plus epsilon by 2. Now this has got positive probability, and so we can write, using the definition of conditional probability, x approximately equal to x and y approximately equal to y divided by probability that y is approximately equal to y. Now I am going to use this kind of heuristic approximation to both the numerator and the denominator. Downstairs I do exactly this thing. Y has some density which I call fyy times epsilon, exactly the same argument. Upstairs we are working with both x and y. So consider the xy plane. I have taken a value x, I have taken a value y, I have taken a small neighborhood around x, a small neighborhood around y. Now x approximately x, y approximately y means I am in this little square. The square has epsilon side here, epsilon side here. Now the probability that I will be in this square is the volume of the tent above this reaching up to the surface of the joint density. Again, by the same argument, I can think of the entire thing as just a box, and the height of the box is roughly f of xy. Of course, this is not a box, it is not entirely flat, but since it is so very small, it behaves almost like a flat constant, and that height is fxy. and the base is epsilon times epsilon. So we shall write heuristically fxy times epsilon square. Now we'll have cancellation and we'll get fxy by fyy, the joint density divided by marginal of y times epsilon. Now observe that this was approximately equal to this, then we called this fellow density. This is approximately equal to this, again epsilon times something, so isn't it very natural that I should call this the conditional density of x given y equal to y. So if xy has joint density fxy and y has marginal density fy, then we define conditional density of x given y equal to y as this thing that we discussed. Now that's the problem. I am dividing by this quantity, so this must not be 0. But this is the value of a density at a certain point. We know that I can change the value of density at any given point to whatever arbitrary non-negative value I want. So there must be something which fixes this value uniquely, and we know that one way of achieving that is by putting a continuity condition. Assuming fy is continuous and positive at y. Continuous fixes this value and I assume positive so that I can really define. And indeed our heuristics works when these densities are actually continuous. In this exercise, I will take xy having joint density given by this formula. It sits over the unit square. You have to find the conditional density of x given y equal to half. In case you have forgotten what that formula was, I will write it down for ready reference. F of x given y, this is the value at which you are finding the density, this is the given value of y, the joint density divided by marginal of y, and in case you do not remember how to compute marginal of y, this is the formula for computing that. You just integrate out the variable that you are not interested in this case x. So just plug in the various things here and compute this quantity.